All right, today's topics are diffraction and interference. They are different properties. They're related. They often occur together to produce some really pretty and striking phenomena that we see in nature. Okay, so first of all, diffraction sounds an awful lot like refraction. It has some similarities. Both have to do with the bending of a wave. If you remember refraction, it's the bending of a wave when the wave enters one medium over another. So, like when light goes from air to water, it refracts. When light goes from water to air, it refracts. Diffraction is the bending of a wave by means other than reflection and refraction. And it's not really changing a medium. It is interacting with a barrier, but it's kind of bending around or bending through the barrier. So things like obstacles, buildings, mountains, uh, stuff like that, openings like doors or slits, or the edges of things. Okay, so here we have a ripple tank, and you can see it's producing equal wavelength of waves on this side of the ripple tank, and the waves are traveling this way. And in a broad opening, you see the wave front, a lot of it goes straight, and then some of it bends slightly. And then the narrower the opening relative to the wavelength, you get a greater degree of bending, and here you get a huge degree of bending. Okay, so at this point, I would usually ask for a volunteer to step out of the room just outside of the door and to a point where I couldn't see them. And I would ask questions like, "Hello, can you hear me?" And they would say, "Yes, I can hear you." Okay, can you see me? No, I can't see you. Okay, so what do you hear with? My ears? Oh, no, no. What kind of wave do you hear with? Sound waves. And are sound waves relatively long or short? They're long. Right. Now, what do you see with? Uh, my eyes? No, what kind of waves do you see with? Light waves. And are light waves relatively long or short? Oh, they're super short. Oh, so they're not able to diffract around the door like sound waves are. Oh, I guess not. All right. Now, are either waves changing media when they're traveling from my mouth to your ear? No, they're both in air. Okay, very, very good. I'd never make a very good ventriloquist. So you can see that or hear that, or that demo illustrates that the size of the wave and relative to the size of the opening or barrier determines the degree of diffraction. Okay, so a shorter wave is going to go through a lot more, or excuse me, a lot more straight and less diffracted than a longer wave relative to the barrier size. So this would be like the sound wave, but even longer, so the sound can bend clear around the opening of the door. And this would be like light. And with the same size of wave, you can see that the broader the opening, the more straight it goes, the less diffraction occurs, and then the narrower the slit or opening, the more diffraction occurs. Okay, now diffraction, it can be good or bad. It can enhance some phenomenon and detract from others. So which waves do you want diffraction to occur with? And if you think about communication waves, like radio waves, AM radio waves are the longest waves we communicate with. And they're hundreds of meters long. So if you're driving around in the mountains and you're listening to an AM radio station, some of you rednecks might listen to AM radio, ha ha. And you can listen to it relatively uninterrupted by even large barriers like mountains. But FM radio stations don't have near that luxury. Regularly, when I drive up to the mountains, I'll be listening to an oldie station on FM radio, and then once you get over Timmerman Hill and down the other side, you lose the signal. And it's in part because of signal strength, but it's mostly because of the inability of FM radios to diffract around that big barrier. The famous commercial, "Can you hear me now? Can you hear me now?" The problem with cell phone reception is you have to have cell towers very close together. relatively speaking. They pretty much have to be line of sight, and you can lose coverage easily because microwaves are what we use to transmit cell phone signals, at least from the cell phone to the tower, and so they don't diffract very well. Okay, other phenomenon are hindered by diffraction. You do not want things to diffract when you are looking at it in a microscope. So here we can enlarge something with and it's 200 nanometers. It's a tiny object, but we would never be able to get it in focus because the light waves are too short compared to the size of the object. So to get a clear image, you want you don't want diffraction. You want a clear shadow of the object. So this is a lot more clear than this. And same with this one over that one. Sonar is similar. Dolphins and bats use sonar. They send out clicks, and then the bouncing of the sound wave off of the object and back allows them to get a really detailed quote unquote image of that object. If it diffracted around the object, they would not get that image. The B-1 bomber, the stealth bomber, the shape of it and the materials used for it allow for diffraction to go around the bomber so that enemies cannot see that plane with their radar.